this is the scope of what we're going to talk about in today's presentation. Data management and data preparation tasks, typically associated with machine learning. So if you're not familiar with Flywheel, I'll give you a sort of a quick overview. Flywheel is an informatics platform focused on imaging, but not limited to imaging. We designed the system to handle virtually any file-based data, so it could involve EMR data or digital pathology, but our strength is around managing and processing complex objects such as imaging. The platform grew out of some work at Stanford University in an imaging core facility context, where the system was used to, or the predecessor system was used to capture data, de-identify data, organize and share data amongst the researchers at the core facility. And it was very popular, and the idea for a more product oriented solution to that problem led to Flywheel. So what does Flywheel do? First off, it's again an informatics platform. It can be deployed in the cloud, very large scale solutions, but it can also be deployed on-prem. About half our customers are in the cloud, half our customers are not. And essentially you can kind of think of a Flywheel as kind of handling four major functions. The ingest or data capture component, which can be multimodality data, also typically involves de-identification. We'll talk a little more about that in a minute. Once data is in the Flywheel system, the heart of the platform is a metadata database, keeping track of all your data, organizing your work so you can find the data you're interested in, let's say for machine learning, and but labeling, classification, search, powerful capabilities for managing research data. Related to that is the computational framework. So we have a solution for automating routine processing, ranging from basic quality checks, format conversions, basic pre-processing, all to full analytic pipelines, and including machine learning workflows, training models, running models, that kind of thing. In Flywheel. And the compute framework also provides extensive APIs for external access and working with your favorite tools, MATLAB, Python, R, whatever you need to use. And then the final bit is around collaboration. Everything, unlike a typical clinical tool, a PACS or a VNA, Flywheel provides a security perimeter that is generally used to enforce IRB compliant or similar project boundaries. So a certain set of data goes into the project, a certain set of users are invited to the project with various roles appropriate to their needs, and the work is done in a secure perimeter. But essentially it's an end-to-end workflow for data management in a research context. So we started in imaging research, and we continue to do a lot of that. But increasingly, with the interest in machine learning and the powerful new techniques available for extracting value from complex objects and natural language processing, other things, there's a lot of interest in machine learning in the context of Flywheel, and our customers are using the system. And this is the purpose of today's talk, is to talk, go through sort of many ways that customers use us in a machine learning context. We're also web-based and very easy to use, so we're well suited to multi-center studies. We did presentation earlier this week on multi-center collaboration, for example. So anyway, so that's the heart of Flywheel. So it's software that helps you manage research and related computation and analysis. As I mentioned, we started in academia. Around imaging core facilities, your NIH-funded grants, multi-center studies. We're growing rapidly in clinical applications, where in a health system, typically maybe associated with the research hospital, customers are using us to extract imaging data from the PACS and the VNA, and cleanse and de-identify that data and make it available to the research community. And we also have commercial customers who are using us to develop AI algorithms. In fact, our largest customer is one of the largest pharmas in the world, using us to ingest vast amounts of data from their various clinical trials and analyze that data for R&D efficiency reasons. But across all of these, machine learning is a thread that is growing rapidly, and that's again the purpose of today's discussion. Just one quick point before we move into the machine learning. One general use of Flywheel, which is closely related to machine learning, is the notion of how you're maximizing the value of your data. You'll see us talk about the hard part of machine learning is not the machine learning, it's the management of the data. And that's also very much in alignment with the NIH FAIR principles, and many of our customers think in these terms. So, how do I make my data findable, metadata search. So again, in the context of machine learning, finding the relevant cases. How do I access that data? I don't want it locked up and continue to be locked up in various systems. I want to be able to access that. So you'll find us being a very open science-based approach with APIs for literally everything, and language bindings to leading scientific languages like Python, MATLAB, and R, of course, all of which are used for machine learning. And then interoperability standards, wherever standards can be applied. And then fundamentally in Flywheel is this notion of sharing data and algorithms, ultimately to maximize the value of reuse of data, but also to support reproducibility objectives. So the Flywheel system is very much oriented around these principles. So let's talk a little bit about how that would apply to machine learning, and you'll see we're going to emphasize the data curation side of this discussion. So if for those of you who are involved in machine learning, I don't think this quote would be a big surprise. And you can find similar quotes and statistics in many places. Doesn't take long. Quick web search will surface this, or your own experience may prove this out. But essentially, most people will tell you the hard part about machine learning is getting the data prepared. This particular stat, roughly 80% of the data is, or the time is spent in preparing the data, which of course comes at the expense of doing the learning and the innovation that you're trying to accomplish with machine learning. So let's talk a little bit about what that entails and sort of how the machine learning lifecycle works. So, broadly speaking, what you're looking to do is find useful data, check it for quality and ensure some consistency. Oftentimes then labeling and organizing the data so you have useful categorizations to train from, and then to go about training and scoring and tracking the provenance of that. In fact, you don't typically train your model once. You're constantly training and retraining and improving. So there's a whole workflow just in that dimension alone. So the challenge is, if you're going to try to do these things, the problem is, especially in a healthcare scenario or medical research scenario, your data typically is locked in, kind of behind many different clinical systems. It could be your PACS or your VNA or EMR, other various subsystems around the system. And if you can get the data, which is not always a given, the data is often not ready to be used. The data is not kind of uniformly organized. Labeling may be inconsistent or absent. There may be unstructured text in the form of radiology reports or similar. And the data may or may not be quality controlled. You may have inconsistent labeling. You may have inconsistent, underlying quality that needs to be assessed and so on. And then, by the way, your data privacy and security concerns didn't go away just because you're interested in machine learning. They're probably more prominent now than ever. So how do you deal with all that? Well, some common needs. You want to get the data in a searchable context so you can find the cases that are relevant to your area of interest and study for machine learning. Quality controls, need to be efficient and fast and clear. Standardizing various pre-processing, generating biomarkers, generating, quality metrics, format conversions, that kind of thing needs to be routine and scalable. Labeling and organization of data needs to be clear and easy. So we'll talk about some automated manual ways to do that. And then, of course, you've got to execute your training. And probably more important than anything is the notion of the provenance. How do you track what you've done and ensure the integrity of what you've created in your resulting models. So this is the scope of what, of things that Flywheel can help with in the context of machine learning. So let's talk a little more in detail then, sort of what might we do. So first, in sort of a typical, this is ISMRM, so we're talking about, typically MR related research, but it may not be limited to MR, might be multimodality research and so on. But increasingly, we're seeing machine learning in the context of imaging research. And you may be in a situation where you're at a health system associated with a research institution, a university health system, and you've got a wealth of data, in your PACS and DNA systems, and creative ideas for machine learning, maybe developing precision care solutions and so on, provided you can get access to that data in a scalable way. So this is where Flywheel can fit in. We can help you ingest the data, essentially creating a repository, help you curate that data, do various image processing tasks, pre-processing as I described earlier, execute machine learning workflows, even support translational testing of your resulting models to see if they're effective. So for example, let's say you come up with a creative algorithm that supplements a certain radiology procedure, maybe you can send back a supplemental report that helps the radiologist. In the event they find that useful and significant, maybe you go for FDA approval, that kind of thing. But Flywheel can help you execute, models in that way and track, whether it's been helpful or not. But generally speaking, what we're trying to do is get data in the hands of the research community so they can conduct their research, including machine learning and personalized care development. So this is the context that we're talking about here. So the first challenge, of course, is getting data out of those systems. So the Flywheel platform has a number of ways to do that. We have automated connectors that can speak DICOM and handle raw data, that kind of thing. We have high performance bulk loading tools that can ingest large volumes of historical data into the Flywheel system. And then on the other extreme, we have very simple drag and drop web uploaders for remote contributors, let's say in your multi-center study context. But part of all of that is integrated de-identification capability in Flywheel, where you can specify a de-identification template or a profile, as we call it, and that can be down to the project level, or it could be at the site level. But essentially, what it's going to do is define how you want your de-identification to take place, and Flywheel will, by the way, do that on the edge before the data is loaded. In most cases, but optionally, you could have a situation where you have PHI in the Flywheel server and maybe some isolated projects with restricted access. And then as you need to make that data available for broader access and research projects, you could essentially clone that data appropriately and de-identify it as needed into those new projects. And there's also some screening capabilities in the form of a quarantine service that can do some scanning and checking to see if any PHI risk has been introduced as data changes in the system. But essentially a complete framework for collecting data and ingesting data that's got configurable de-identification to help you scale data collection and while respecting the data privacy constraints and concerns that everyone should have. As the data gets loaded into Flywheel, this is kind of starting the point of organizing your data, particularly if you're thinking about multimodality research involved, for machine learning. Flywheel is going to help you organize that around some uniform concepts. So you're going to have projects, as I described earlier. You'll have patients or subjects in your research. You have time point exams. We call them sessions, a little bit of our imaging bias there. But those time point exams, sessions, encounters can be made up of any data in Flywheel. So it could be imaging data, it could be non-imaging, EMR, digital pathology, other types of data, EEGs, et cetera. And the way we do all of that is we just provide enough structure to keep you organized, but we provide extensibility so that you can meet the needs of your unique project. So you can attach files at any level of this hierarchy. You can attach custom metadata. Technically, it's done in the form of JSON objects that you can attach to anything, and then at that point they become available for search in the database. So as we go through some use cases where we're selecting interesting cases, let's say, for example, we wanted to extract some features from a radiology report and attach it to the image data. You could attach those structured features to that radiology report, and then go search for radiology reports that have the features that you're interested in. And then another feature of Flywheel is, and this is relevant to the machine learning workflow and training, is we track every material processing step. We call it an analysis object, but essentially it tracks all your inputs, your outputs, configuration options, who did it, when it happened, did it succeed, did it fail, any logs that were produced, that type of thing. So it's very useful as provenance for your training or your image processing pipelines. So let me give you some examples then what happens when the data is ingested into that structure. So one area we can help with machine learning is to start to label things in a consistent way, so you can find samples or cases that are relevant for your particular machine learning task. So if you're familiar with MR pulse sequences and protocols and so on, you often get a wide variety of scan types and with kind of a variety of labeling schemes, but you may want to eventually figure out, I just want a set of T1 weighted structural images for development of a quality control algorithm or something, and regardless of all the various labeling schemes that exist in the database. So Flywheel has a framework for classification. And it's extensible, and you can add features to it and so on. But generally speaking, you can take all these terse labels and convert it into, this is an MR, T1 weighted structural image, regardless of how it's labeled. So the way that works is we have a gear, a component that is defined to do that. It extracts the various DICOM attributes, the labels. Part of its job is to index that metadata in the Flywheel database. But it also sets this classification value, and you can set this up on an automated basis. So the rules in the upper right here are basically saying, when a new DICOM lands in the system, run the DICOM classifier. It's the very first thing that happens, and it's fully automated. So data lands in the system, it runs this algorithm, puts the metadata in the database, and then sets this automated labeling so that later you can come back and find similar images regardless of whether they're specifically part of a T1 Bravo sagittal sequence. So that's an automated labeling scheme that helps a lot. A similar thing that you can do is kind of with quality control. So let's say you're concerned about the quality of images. You want to understand the quality of the images before you use them for your machine learning. You may want to run various quality metrics on the data. So in this example, I'm showing the use of MRI-QC, which is a BIDS app that works on functional or structural images. And we've set up a rule here on the left that says whenever I have a NIFTY that arrives, by the way, Flywheel can automatically convert DICOMs to NIFTYs, so this might be the result of that transformation. But when a NIFTY arrives and we've classified it as structural or functional, and it's not an in-plane, then go ahead and run the MRI-QC, because those are the preconditions for running MRI-QC. So then on the right, what you'll end up with is a series of reports that give you some visual tools to inspect the quality, but also a set of metrics here on the right, all data-based and queryable, so you could find images that meet or exceed certain quality specs for your use in your machine learning. So automating quality. The other thing is you may want to annotate images to identify certain features. Let's say you're looking for glioblastomas or tendon tears in a MSK study or that type of thing. Flywheel has integrated imaging tools with radiology grade features. You can, for example, set up custom labels to identify, as you draw ROIs, what do those things represent, a lesion, a tumor, a glioblastoma, whatever it is. And that's totally configurable. And then let's say you can kind of see on the lower right here, there's a qualitative summary that's also configurable. So instead of using a spreadsheet and tracking the results of your reads, separately, Flywheel can just define a form that goes in the viewer, and if you find it a full thickness tear of the supraspinatus, in that case, it'll record that in the metadata, and then all of that becomes searchable and usable for finding cases that are of interest for your training, or to assist your training by identifying the location of specific features, as in the case of these specific ROIs and labels. And a little more on that is that Flywheel can also be set up to support blind multi-reader studies, that can be distributed as needed. So if you kind of think you have a project and you have a set of readers, radiologists who are going to come in, or expert readers of some sort, and they simply need a work list. Say, what are the cases I'm supposed to read? The data is redacted and blinded, but they see the images, they draw their ROIs, and those ROIs and labels and qualitative summary data that I described earlier get recorded in the database, and all of that is accessible via the APIs and is searchable and easy to access for creating features for your training. So again, that's how that can work. It's simple as just annotating things, but you can also even set up workflows for blind multi-reader studies. So with that kind of background, maybe you have a question like, hey, let's find all the images and related, EMR data, let's say for glioblastoma patients who have a glioblastoma larger than, N in size, and then train a model on it. So how do you deal with that kind of scenario? Well, one thing you might try is using natural language processing to read radiology reports and extract features of interest, and then database those in Flywheel so that you can find the cases that are of interest. So Flywheel gears, our plug-in pipeline components, can certainly be NLP algorithms. We have people on our team, for example, who recently participated in development of an NLP algorithm to read TBI factors from radiology reports. I think it identifies 27 specific features from radiology reports and put some structure behind those. And it deals with the negation, issues like, does it, yes, we know it was the feature was referenced, but does it exist or not exist? Based on the language used in the report. So that's an example, and you can use it more broadly to extract general features, or in this case, it was a very specific use case. But that kind of thing can be implemented as gears in Flywheel. The resulting structure then goes into the Flywheel database where it's now available for search. So we could find glioblastomas that are referenced in those radiology reports and find cases in that way. We could also, by the way, reference ROIs. So the way all this works is Flywheel provides a very powerful search engine built into the tool. And so any of the metadata that I've referenced, from radiology reports or DICOM tags or other sources, forms, that you might enter, but also the ROIs are searchable. And so we kind of have two modes of search in Flywheel. One is, you kind of see it here in the illustration on the left, there's sort of these filters. It's like buying a brain on Amazon. You go in and say, well, I'm looking for, MRs or PET scans or whatever, and for females between the ages of X and Y, and then you can filter down, I just want the NIFTYs or whatever kind of data, and that filter approach is super easy to do. However, we also have an advanced mode where you can build complex and or type queries, and you could build a query like the one I described earlier, where you say, well, I'm looking for any ROIs that are labeled as glioblastomas. You could use it for patient-reported outcomes, and with different ranges. But essentially, it's a SQL-like query structure, and then the tool provides a visual builder, so you can easily find the metadata. There's many metadata values, of course, so you could. So our goal may be to eventually train a model off of this data, so you can add it to a named collection and come back and reference that collection at any point. You could download the data immediately to your server or your desktop, which would be a classic way to do it. Set the files up physically on a folder somewhere, and then run your training algorithm against it. But you can also find yourself copying a lot of data unnecessarily. So Flywheel has introduced a concept called a training set, an ML training set, and it's a virtual way to download the data. So essentially what it does is it creates a JSON file pointing to all the selected data and can snapshot the labels that you've selected. And then your trainer just has to open up that file and iterate across those items, and Flywheel will authenticate you to the data, and then you can access the data in place. So you can avoid having to copy and set up lots of folders and physical time to set those folders up. Flywheel will just give you a reference to the data that you've selected. So anyway, so powerful search, easy to select the cases of interest, find the files. You can search by ROIs, you can search by any metadata attribute. So let's talk a little bit about machine learning specifically then. So we've prepared the data. So a big part of Flywheel, as I've just described, is preparing the underlying data to be ready for machine learning. But you could also use Flywheel to train your model. So this GEARS framework, which is really, an OCI or Open Container Initiative compliant container, can run any, application code that you need. Classically in Flywheel, we use GEARS for image processing, pre-processing pipelines, that kind of thing. But you can certainly deploy training algorithms in them, or you can create a gear that is a proxy or an interface to an external training algorithm that you may want to use. So let's say you use a hosted cloud service for very large scale training and GPU access, that sort of thing. Either way, a gear can be used to help you train those models, and it essentially will track everything that you've done. What inputs did you use? All the results. This provenance document I described earlier would be there, and so you can kind of track your various iterations and the relative performance of them, that kind of stuff. And we don't have a bias towards which tools you use. I just illustrated a few here. Obviously, TensorFlow and PyTorch are very popular. Scikit-learn, other tools that people use. And then we have some experience with the Google ML suite as well, and I'll show you a quick example there. But basically, Flywheel can help you prepare the data, can help you train and retrain the models, but also, and I alluded to this earlier, the idea of setting up translational testing. So let's say you define a model and you want to evaluate whether that model is useful on new cases coming out of the PACS. You can set up a DICOM listener that says, hey, well, send me those, that type of head scan, let's say, and apply the model, and then, generate a resulting output of, let's say, a report, a PDF, maybe wrap it as a DICOM and send it back immediately to the PACS. So the radiologist has a new supplemental report, leveraging your new algorithm to see whether it's effective or not. So that would be a range of ways Flywheel could be used in machine learning. We did an interesting example with our friends at Google, where they've been making a lot of progress on their AutoML vision tools. And, as I mentioned earlier in Flywheel, we have a large number of data sets that are, we classify everything almost by default in Flywheel. So we had a very large set of images that were already classified as, in various forms like T1 weighted structural or diffusion scans, or that sort of thing. So we ran some tests using Google's AutoML vision. So this is a case where we had a gear that was an interface to a cloud-based training system. So the gear kind of looks for the inputs. So we selected some via search, we pull those in, and then the first thing we run into is that the AutoML tool doesn't know anything about DICOMs or NIFTIs. So we do some conversion to convert it to JPEGs or PNGs or whatever it is that it takes. And then but we have the classification values and we have the images. So we package those up, upload them into the training tool, then execute the training process, and then we get a resulting model back. And all of that is fully documented and tracked inside of Flywheel. But the exciting thing was that their algorithm actually did a pretty good job. The process scored pretty high on various runs under different types of classification. So this, again, I'm just illustrating an example of the kinds of things that you can do. So if you have a favorite external tool or you're building your own training tools, Flywheel can help you automate these things. But this is just an interesting example of how we used it. So maybe in conclusion, we think we have a very powerful and flexible, scalable tool for, the machine learning lifecycle. So, if you're back to, finding useful data, we can ingest and de-identify the data. We can help you classify. We have search to help you find the cases. Earlier I mentioned also the, NLP type stuff to identify features could be part of that process before the search. We can help you with quality and consistency, standardizing your pipelines, standardizing your quality controls, configuring that in an automated way through templates and rules. Labeling and annotation, we have automated classification, but we also have the idea of, having, attaching any user-defined metadata, which again may be like the structures identified in a radiology report, image annotation with persistent ROIs that are all searchable and configurable, blind reader study capabilities. And then we have automation and tracking and reporting on all of that. So that was the intent of today's presentation, was to just give you a feel for how Flywheel can be used in the context of machine learning and some of the features that help you along the way. I might add that the nice thing about Flywheel is that it's very much an open science-based approach and totally extensible. So we have a nice web-based user interface for administering your projects and exploring your data, visual inspection, all that type of thing. But technical users like ML developers or image processing algorithm developers like the platform, because we provide APIs for literally everything in the system, and it's totally extensible. So we're tech friendly in the way we approach it from an open science point of view. So anyway, I'll stop there. Hopefully that's a useful overview of how we can help you with machine learning. I'll maybe turn it over to Esther and see if we have any questions at this point.
Yes, I welcome any additional questions to our Q&A feature in Zoom, but could you go through an example or talk about how you would bring in a neural network to Flywheel?
Sure. So a neural network would typically be a model. Well, let's back up. So you could train a neural network using Flywheel, as I described earlier. So let's say you might identify imaging features that you want to run through a neural net, and you could train a model that result using a neural network technique, and then you would get the resulting model neural network back and could deploy it as a gear in that translational testing scenario that I described, for example. Or you may have an existing one, and we have customers who are doing free surfer like brain segmentations using neural networks, for example. And you could essentially replace one algorithm with a neural network and plug it in as a gear if you're comfortable that it's production ready, and just deploy that algorithm as an alternative segmentation tool or something in that nature. So Flywheel doesn't really care whether you use neural networks or other techniques. You can train things, you can run things, run models. So and Flywheel, one thing Flywheel can help with is we're very good at helping with the scalability of these types of tasks. So if you're running a large number of image processing tasks, we can do elastic scaling to run hundreds of these things in parallel. Let's say you needed to do free surfer segmentation on a lot of images, we can run many hundreds of those things in parallel, and then tear them all down when we're done and get through the work faster. The other thing from training a model like a neural network, Flywheel can be configured to run gears on just about any configuration of hardware. So we can support multiple clouds in the same environment. We can support your high performance computing cluster architectures, but we can also send gears to be executed on let's say a dedicated GPU, multi GPU box or something that would make such tasks go really quickly. So the nice thing about Flywheel is it kind of orchestrates manages the data, but can also orchestrate the computation to the right resources, including GPU boxes and things like that.
I see. Our next question is whether it's possible to bring in publicly available data sets if you're working on machine learning on those public data sets.
Sure. The answer is yes. We have a lot of customers who pull in data from NIH data sources or similar other foundations and so on, and we make that very cost effective to pull that data in and index it and make use of it. We're also starting to see some customers who are using Flywheel to share those types of data sets across various labs. So instead of having 5 copies of, I'll pick the human connectome database as an example, and that comes with A, a lot of data, and B, a lot of obligations to manage and control access to it. If you're a research institution, do you need 5 copies of that or more? so people are starting to use Flywheel to take that kind of thing and centralize it and share it more cost effectively, while maintaining the obligations around access controls and that type of thing. So yeah, public data sets, and this may be an area in the long run where Flywheel could help if, with the right cooperation with NIH and others, we could conceivably host those data sets centrally and make life easier for people. It's kind of one of those things we have on our roadmap, but we're working our way towards.